In this video, we're going to go over section 4.2 on general vector spaces. So the idea here is that we're going to abstract the notion of a vector space by taking the key properties of a vector space as axioms and stating that any object with the appropriate operations that satisfy these properties is considered a vector space. So basically, you want to think about how vectors in Rn behave with respect to vector addition and scalar multiplication, and try to transfer those ideas over to other types of objects so that we can carry over our understanding of the standard vector spaces, Rn, to much more general settings. So in here we're focusing on vector spaces, but this idea of abstraction applies to any kind of object in mathematics, where you take the key properties and you try to generalize it to other settings. Okay, so so let's look at the properties of a vector space, right? So a vector space consists of a set of vectors and two operations, vector addition and scalar multiplication, and the set together with the two operations has to satisfy these 10 properties, right? So 5 properties corresponding to vector addition, and then 5 properties corresponding to scalar multiplication. So the first property is that it's closed under vector addition. So basically the idea is that if you take two vectors in your space and you add them together, the resulting vector should still be in the same space. The commutative property is that it basically just says that it doesn't matter which order you add the vectors, it's always the same. The associative property carries this over to 3 or more vectors. The additive identity says that the vector space should have some kind of zero vector, where if you add it to any other vector, the vector stays the same. The additive inverse says that you can always cancel a vector from using vector addition. There's always another vector that can cancel out a vector from vector addition, and this is called the negative of the vector. And then there are corresponding properties for scalar multiplication, and they're similar to the ones, again, that you're familiar with, right? So you can distribute a scalar over the sum of two vectors, or you can distribute a vector over the sum of two scalars. And then here's the associative property for scalar multiplication, and then the scalar identity says that if you take the number 1, you multiply by a vector, the vector stays the same. Okay, so one thing to be careful about how a vector space is defined is that it's not just the set that forms the vector space, but the set together with the two operations of vector addition and scalar multiplication. Right, so all three together need to be described to have a vector space. And then the 10 properties must be satisfied for those operations. But usually the way we define vector addition and scalar multiplication is the standard way for the spaces that we'll discuss. So the first example of a vector space is what we discussed in the previous section, right? So Rn with the standard operations of vector addition and vector and scalar multiplication is a vector space, right? So vectors take the form n tuples where each coordinate is a real number. And so I'm not going to go into detail, but essentially all the 10 properties are satisfied because the operations for vector addition and scalar multiplication are essentially done coordinate wise, and because each coordinate is a real number, the properties for real numbers carry over for the entire vector. Okay, so we've already discussed Rn, so let's look at other vector spaces. So the second kind of vector space we're going to talk about is matrices. So I'm going to write M sub 2 by 3 is the set of all 2 by 3 matrices, where the operation of vector addition is just standard matrix addition, and scalar multiplication is just what you do for scalar multiplication of matrices. And the vectors of the 2 by 3 matrices is just of this form where you have a 2 by 3 matrix. Okay, so essentially you can think of it as a vector where each entry of the matrix forms a coordinate of the vector, right? So a 2 by 3 matrix has 6 coordinates, right? You can think of this, say, like as the first coordinate, this is the second coordinate, this is the third coordinate, this is the fourth coordinate, and this is the fifth coordinate, and this is the sixth coordinate. So again, each individual entry of the matrix is a separate coordinate for the vector. And basically, again, the operations satisfy the 10 properties because we're familiar with how these operations for matrices work. So here I've listed the vector for 2 by 3 matrices, but in general, the set of m by n matrices is also a vector space by following the same idea, where an m by n matrix has m times n coordinates. Again, each of these coordinates is a real number. So as usual, we're gonna look at various different objects used in different contexts. So for matrices, here I'm specifically talking about a matrix thought of as a vector, right? So later on we'll think of matrices as linear transformations between vector spaces, and the individual columns itself can be thought of as vectors, or the individual rows themselves can be thought of as vectors, right? So be careful how you think of the single object used in different contexts, and what is meant, what we mean in each of these cases, right? So looking at this matrix here, the whole matrix itself can be thought as a vector with 6 coordinates. The first column can be thought of as a 2-dimensional vector with 2 coordinates, right? So this is the first coordinate, second coordinate. The second column can be thought of as a separate 2-dimensional vector. And then the third column can be thought of as a separate 2-dimensional vector, right? So each individual column gives you 3 different vectors. Or looking at the rows, each row is a 3-dimensional vector, right? So 3 coordinates here and 3 coordinates for this row. So we're going to look at matrices in different ways. So be careful about the context that we're using any of these particular objects. Okay, so matrices form a vector space. And then the next example we're going to talk about is sets of polynomials as vector spaces. So I'm going to write P sub 2. This should say degree 2. This is a typo. This should say degree 2. So P sub 2 is the set of all polynomials of degree 2 or less, where the vector addition is just the standard polynomial addition, where you add polynomials together and collect like terms, and scalar multiplication is just multiplying the entire polynomial by the scalar. Right, so here, if you look, I take two polynomials with degree 2 or less, right? So a sub 2 x squared, a sub 1 x plus a sub 0, right? So and then here q of x is a different second degree polynomial. Right, so essentially the coefficients, right, so the coefficient of x squared is playing the role of the first coordinate, the coefficient of x is playing the role of the second coordinate, and then the constant term is playing the role of the third coordinate. Right, so you can see that this is very similar to just having a three-dimensional vector. And similarly, this polynomial here, again, you can think of this, the individual coefficients as the coordinates. Right, and so when you do the standard way of polynomial addition, right, so again, it's just collecting like terms and then adding the coefficients together. Right, you can see that we're just adding the corresponding coordinates together, and this is exactly how you do it for other kind of how you do it for Rn, right? So, so if you really just think about it, these are very similar to three-dimensional vectors, just represented in the form of a polynomial. Okay, so these are a couple of examples of different vector spaces from the standard Rn that we're going to be dealing with. So at the top of this page, in this little brown box here, is a summary of various different kinds of vector spaces. I mean, these aren't all the possible vector spaces. I mean, there's an innumerable amount of different kinds of vector spaces you can think up, but these are ones that you might already be familiar with, right? So we've already discussed Rn as a vector space, and we've also discussed matrices as vector spaces. So P sub n is the set of all polynomials of degree less than or equal to n. But then you can also take the set of all polynomials as a vector space, or the set of continuous functions. On a closed interval, or the set of all continuous functions that are continuous over the entire real line. So these are also vector spaces, where the vector addition is just adding two functions together, right, in the standard way, and the scalar multiplication is just taking a function and multiplying it by a real number. So those two operations are just calculated in the way that you're used to. But one thing to be careful about these three particular spaces, right? So vector spaces of continuous functions, or the vector space of all polynomials. I mean, we haven't really discussed what the dimension of a vector space is, but when we do discuss the dimension of a vector space, these three vector spaces are examples of infinite dimensional vector spaces. Whereas, I mean, this course focuses mainly on finite dimensional vector spaces, because for infinite dimensional vector spaces, things you have to be a little bit more careful about the technicalities of infinite dimensional vector spaces. For finite dimensional vector spaces, it's a little bit more straightforward. So we mainly focus on that in this course. Right. So in terms of dimension, R is one-dimensional, R2 is two-dimensional, R3 is three-dimensional, Rn has dimension n, P sub n has dimension n plus 1, M sub m by n has dimension m times n, and this has dimension n times n. You basically just think about how many coordinates you need to represent a vector in that space. Right, so P sub n has the n powers of x plus the constant term, right? So that's n plus 1. Okay. So here we look at some examples that fail to satisfy all of the properties for vector spaces. Right, so you can't just take any arbitrary set and think of it as a vector space. Okay, so let's look at these examples. Right, so here this set is described as the set of x and y coordinates where both x and y are non-negative. So basically it's the first quadrant plus the positive x and y axes. Right, so this is first quadrant plus the positive x and y axes with the standard operations of vector addition and scalar multiplication. So the claim is that this is not a vector space. So first let's think about the two closure properties. Right, so is it closed under a vector addition? So in terms of vector addition, you can see that it is closed under vector addition, right? Because if you take two vectors that have non-negative coordinates and add them together, the coordinates will stay non-negative, right? So I mean, adding two positive numbers is a positive number, and adding two positive y coordinates is also a positive number, right? So you can see that it is closed under vector addition. But what about scalar multiplication? Right, so in terms of scalar multiplication, the scalar you use can be any real number. Right, so you can see that this set is not going to be closed under scalar multiplication because if I take a negative scalar, right, a negative times a positive is going to give me a negative number, right, which will no longer satisfy this condition. Right, so So say if you take C to be, say, -2, and my vector V to be some vector in here, so let's say 2, 4 or something, then so let's call this, what should I call this? Let's just call this V. But it's not actually a vector space, right? So so this is in my set V, but C times V is -2 times 2, 4, which is -4, -8, and this is no longer in my set because it doesn't satisfy these properties. Right, so this says that V is not closed under scalar multiplication. And so because it fails this property, that means it's not a vector space. But I mean, there are other properties that also fail, right? Because there's no additive inverse because you're not allowed to have negative coordinates and so on. Okay. So let's take a look at the next example. So we have the set of all polynomials that have exactly degree 2. So the claim is that this is not a vector space. So the reason is because it's not closed under vector addition, right? Because you can add two polynomials where some of the terms cancel out and you result in a polynomial of lower degree, right? So here it's not closed under vector addition. So say we just come up with an example that cancels out the x squared term. So say p of x is x squared plus 2x minus 1. Say q of x is minus x squared minus x plus 3 or something. Then, right, so both p and q have degree 2, but if I add p of x plus q of x, right, so that's x squared plus 2x minus 1 plus minus x squared minus x plus 3, right, so the x squared cancels out, and then 2x minus x is just x, minus 1 plus 3 is plus 2, so now this has degree 2, has degree 1, right, so the result of the sum doesn't have degree 2, so it doesn't satisfy this condition, right, so that means it's not closed under vector addition. So this isn't a vector space. Okay, so in this example, we're going to look at a vector space that has the same set as one we're familiar with, right? So R2, but instead we're going to change one of the operations, either vector addition or scalar multiplication. In this particular example, the scalar multiplication is still the standard one, right? So they're the standard way we typically do it. However, the operation for vector addition is changed to a non-standard one, where it's defined in this way, right? So you take two vectors, so x1, y1, and then x2, y2, and if you add them together, the result is to take the first coordinate in the first vector, and the second coordinate is always 0. Okay, so let's see what happens with these operations, right? So if you think in terms of the closure property for addition, well, obviously the closure property for scalar multiplication should still hold, right? Because it's the standard one. But the closure property for addition also holds, right? Because any vector in R2 is just a pair of coordinates where both coordinates are real numbers, right? So you can see that the resulting vector here, x1, is a real number, and 0 is also a real number. So the result is still in R2. So there's nothing wrong with the closure properties in this case. So if we want to show that it's not a vector space, we have to look at some of the other properties. Okay, so let's look at the commutative property. So we'll see that the property 2 fails. Which is the commutative property, right? Because I mean, if you think about it, if you add it this way, you take the first corner of the first vector, which will be x1, but if you switch them around, the first corner of the first vector is then going to be x2, which might not be the same as x1, right? So so to show any property fails, we just need to come up with a single example, right? So so let me take, say, the vector 2, negative 1, and say 1, 3. So it doesn't have to be this particular example, but we just need to come up with some example where it fails, right? So if I add this together, what do we get? Right, so the 2 is, so this is the first vector, right? So this is playing the role of x1, this is playing the role of y1, and then this is playing the role of x2, this is playing the role of y2, right? So the rule for the addition is to take x1, which is 2, and the second coordinate is always 0, right? So the result of this would be 2, 0. But what if I do it the other way around, right? So 1, 3 plus 2, negative 1. Right, so now this is playing the role of x1, this is playing the role of y1, playing the role of x2, playing the role of y2. Right, so again I take x1, but now x1 is a 1, right? So you can see that when I add it one way versus another way, I don't get the same result. And so these are not the same. And so property 2 fails. The next property is the associative property. you can see that the associative property is going to be okay. So I'm not going to go into detail for that. But say you have 3 vectors, right? And the result of the sum of this is going to be the first coordinate of the vector u, right? And then the result of this sum is going to be the first coordinate of u. But then when you add it with w, it's also still going to be the first coordinate of u. Right, so the associative property is going to be okay. But what is the next property? Property 4. So the 0 vector. So that if you add 0 to it, you get the same vector back. I mean, you can see that this is going to fail, right? Because if you add something here, right, the second coordinate is always going to be 0, but y1 isn't necessarily 0, so you can't recover the original vector by adding the 0 vector. So property 4 fails, right? Because if you take, say, u to be the vector 2, -1, then u plus 0 for any possible 0 vector, which I'll call x comma y, right? So it'll look like 2 comma -1 plus x comma y. But then the rule says I take the first coordinate of the first vector, right, which is 2, and then the second coordinate is always 0. But this is not equal to u, so I can't recover the original vector. So property 4 fails. But one thing to be careful about with the 0 vector is because the addition is defined in a non-standard way, the 0 vector might not be the standard 0 vector, right? So 0 comma 0. That's why here I didn't take the standard 0 vector, but I took an arbitrary 0 vector, and you can still see that the property fails. So that's one thing to be careful about. So because vector addition is defined in a non-standard way, the 0 vector also be non-standard and may not necessarily be, in this case, 0 comma 0. But because here we've shown that property 4 fails, this set doesn't have a 0 vector at all. So because there's no 0 vector, there's no sense in looking at property 5, right? Because there's no notion of cancellation. So basically property 5 fails because 4 fails. In terms of the other properties 6 through 10, they're described for scalar multiplication, but 7 and 8 do involve addition. So we can also take a look at that, and we can see that property 8 also fails. Right, because I can take C to be, say, 2, D to be -1, and U to be, say, 2 comma -1. Right, so C plus D times U would be 2 plus a -1 times 2 comma -1, which is just 1 times 2 comma -1, which is 2 comma -1. And if I distribute it, so C times U plus D times U, so what is that? So that's 2 times 2 comma -1 plus -1. Let me just write it as -1 times 2 comma -1. So that's 4 comma -1 plus -2 comma 1. But you have to be careful, alright? What is the rule for vector addition? It's taking the first corner of the first vector, right? So, because this is x1, this is y1, this is x2, this is y2. Right, so taking the first corner of the first vector is 4. And so you can see that these are not the same. So property 8 fails. I mean, in general, in this kind of problem where we want to show that it's not a vector space, you really only have to show that at least one of the properties fails. But in this case, we looked at a few different properties because to give you an idea of how each one might fail. In general, in this kind of problem, it's not always obvious which of the properties may hold or which of the properties may fail, and so you have to play around with some examples to get an idea of which properties are okay, which properties fail. And one other thing to note is that in property 5, where you're talking about the additive inverse, again, because vector addition is non-standard, the additive inverse might also be non-standard. In this case, it doesn't exist at all.